All right, so we are today looking at some applications of exponential growth. So everything we do today is going to be a scenario where something is growing over time. Tomorrow, or for some of you guys, will probably just watch this on the weekend. Tomorrow we'll do a few examples where something decays or decreases over time. So we're going to start with a classic application, population growth. So we're going to use bunnies in this case. Um, a brand new family of 10 rabbits. Now, the population doubles every year. Maybe I should reword this, and maybe it shouldn't be a family of rabbits. It should be 10 stranger rabbits who don't know each other. Otherwise, that sounds kind of bad. But anyway, whatever. Whatever. 10 rabbits settle down to a briar patch. The population doubles every year. I'm actually going to do part B first. You guys could do part B. You guys could have done part B in like grade 5. We have 10 rabbits that start, and then every year, use a different color. 10 rabbits to start, and then every year the population doubles. So after year 1, there would be 20, and after year 2, there would be 40, and we'll fill the graph up. 3, there'd be 80, 4, 160. And if you connect those with a smooth curve as best you can, shockingly enough, it is an exponential function. But what we want to do today is we want to take scenarios and model them with a function, with an equation, and then do some stuff with those equations. Now this one's not too bad at all. So I'm going to use, instead of f of x, I'm going to use p for population and t because I'm kind of using time. You can use whatever variables you want. I'm not your dad. But I'm going to use p for population and t for years. And you guys basically have 3 things to fill out. I'm going to create a little fill in the blanks for myself. And t divided by, so it's just like basically like your warm-up where you have 3 blanks to fill. This time the scenario tells you what those blanks are. So our scenario says we have 10 rabbits initially, so our initial value, we called it our A value, is 10. And then the population doubles every year, so doubles meaning our base will be 2. And if it doubles every year, then it would be t divided by 1. So I guess we don't really need the last blank. You can just erase it there. There you go. We've modeled our first scenario. Population growth is a classic application of exponential growth. Are you guys okay with what we did there? I could have said triples every 5 years or quadruples every 20 years. Same idea, initial value and information about the growth rate. But here's what you guys are in both courses. Here's what you guys are expected to be able to do with after creating a model. So you create the model, you're expected to be able to do plug and play. What do I mean by that? Well, let's find the population after 5.5 years. After 5 years, it would be easy enough. It would be exactly 320 according to our model. And 6 years, it'd be 640. But what happens in the middle? Well, we can use our equation. So we're going to find the population after 5.5 years. This is nothing crazy. It's just using the formula we just created, 10 times 2 to the power of 5.5. And our expectation here is that you just put this into a calculator. We don't need to, although we could, 5.5 is like 11 over 2. We could rewrite that as a fraction and use our exponent rules. But the idea with these questions is we're just slam it in there. And your calculators can do this all in one step. So you guys do it with me too. And I'm going to round to the nearest whole rabbit. I got like 452.5, but like that seems a bit morbid talking about half a rabbit. So let's just round that. You guys okay if we round that to 453? You guys get that as well? 4? Maybe. We just won't go there. So that's the first thing you guys should be able to do with the model is just do some plug and play. Now, we just showed after 5.5 years, there's 453 rabbits. But what if we wanted to do something else with that equation? We wanted to find, what if we wanted to find a time when the population is 10,000? So essentially, we're saying the p at what value is going to equal 10,000. Now, currently, you guys actually do not have, I have space, I'm just going to jot this down. So this is like taking 10,000 and putting it in for p, and that would be 2 to the power of t, and asking what value of t gives you 10,000. You guys currently don't have an algebra tool to get the t by itself. You know, if it was t plus 10, you would just subtract 10 from both sides. If it was like 2 times t, you divide both sides by 2. But you guys don't really know the opposite operation yet for raising something to the power of 2. That's a grade 12 university, a grade 12 functions a thing. The grade 12 functions people just learned that. For you guys, the expectation is you use guess and check to make an estimate. So the idea here is not to solve exactly for t, it's to make some reasonable, intuitive guesses and then eventually get something close to 10,000. So we know it's more than 5.5. Can you guys, I'm sure with all 8 of us in the room here, I'm sure we could get pretty close. How close can we get? Now, I'm going to just suggest a strategy for you. Obviously, 5.5 is too small. What about 12? I don't know. What is it after 12 years? I'm not going to write down I'm just going to write down my answer. 10 times 2 to the power of 12. Okay, so 12 gave me 40,960. Obviously, way too big. Did anyone get any closer? So if that's too big, this is you. You tried something, and then it's not little, who's the Goldilocks, right? It's like too hot, too cold, just right. Obviously too big. Let's try something smaller. I don't know. How about 10? And if 10 is too small, we'll try something larger. 10 times 2 to the power of 10. Actually, that was pretty good. 10 gets us pretty close. Did you guys get 10,240? It's pretty good. Can you guys do better? Can you guys see the nearest tenth of a year? Can we get any closer to 10,240? Maybe a bit less. Can we try? I'm going to try like 9.9. Is that any closer? 9,554. So actually, to one decimal place, 10,240 is about as good as we can get. So I would just wrap this question up and I would say, therefore, it takes about 10 years. All right, so 3M, 3U doesn't matter. When you're estimating like this, it's just educated guess and check. That's the goal for this course. If you take 4U functions, then we'll find ways to do it exactly. Okay? That's it. That's what we're doing today. We're making a model and to do these 2 things with it. Now, let's do one more twist here. Let's change it. So instead of having information about how our population changes after 1 year, what if we, in this case, have 100 rabbits settling down and tripling in size every 4 years? So P of t equals, and then again, can you guys fill in our blanks? Create a model for this one. We won't do anything with this model, but you guys can actually create a little fill in the blank action. Can one of you guys fill in the blanks for me? Skylar. T over 4. Exactly. Okay, so this is the expectation. I give you a scenario. You create a model, and then you do either one of these two things with me. You plug and play, or you do some educated guess and check. Let's look at another application. Population growth is another. Finance is another. After the Christmas break, we are doing financial math. But this is just these two examples are just a little teaser into that. So, um, uh, this is just like a approximation here. Like things like sports cards, antiques, stuff like that. They don't follow a strict rule where they increase in value by a fixed amount. But like for our purposes, it's useful to kind of think they do. So let's look at this example. Bort. Do you guys even remember Jose Batista? It's like 10 AJ does. Okay. Bort bought a Jose Batista rookie card for $20, and he thinks that will double in value every 5 years. So, can you guys create a model, and then can you find what the card will be worth after 48 years? I'll suggest some variables to use. I'll use A for amount, and I'll use T for time again. But you can use whatever variables you want. I would just advise that you choose variables that just make sense. Like J and Q would be a little weird. Okay, and then you just create your model. It's always this little fill in the blanks. And then I have a tip for you when we're doing part two. Who's got the model for me for this one? Jillian, you got this one? 20. Two for doubling? T over 5. All right, so I feel like this part of the lesson, you guys we're doing very well with the modeling, with graphs and stuff. So I think this is going well. Now, when your equation looks like this, just a small tip for something like 2. So 2 is just saying, okay, what's the amount after 48 years? It's just a plug and play, but just be careful doing a calculation like this. In the exponent here, we have 48 divided by 5. If you're super comfortable on your calculator, you can do all that all at once, just being careful with brackets. My advice is just do the 48 divided by 5 first. Do it in 2 steps. 48 divided by 5 is, don't tell me, 9.6. And then from there, calculator can handle that no problem with no brackets or anything. But yeah, if you're feeling adventurous, give that a try all in one step. I mean, it just requires a few brackets. I'm sure you guys could figure it out. You're all intelligent people. But I'll always do it this way myself. All right, so I got 15,520, and because it's a money question, I'll round to the nearest cent, 94 cents after 48 years. I mean, it probably won't, but I mean, this is a way we could model things that appreciate over time. Do you guys get the same value I got? Okay. So nothing really new. It's just working with this kind of model. Be careful with the calculation. Okay. And then one more example too with you guys, and then anything else is really just overkill. It is kind of the same things, but do got to talk about some finance stuff and review some percentage stuff. Because this question, Bort's credit card balance isn't doubling or tripling or anything like that. It's increasing by an extra 4% every month in this case. So we're going to model the amount on his credit card. I'll use A again for amount. Why not? And just to be different, why don't we use M for month? You can use T for month. It's still time. But I'm just mixing it up. You can do whatever you want. So Bort puts 200, 2,500 on his credit card. Now, I think everybody understands, okay, that's our initial value. And it is every month, every 1 month, he's charged an extra 4%. So it's just every 1 month. So in our exponent, we'll just have M. It's not every 2 months or 3 months, so it wouldn't be M over 2, M over 3. It's every 1 month. But the question is, what do we put in our base? So we'll have to time travel back to grade 9 math when Miss Answer is, or whoever was your math teacher, or me, did percentages and financial math with you guys. Anybody want to put themselves out there and hazard a guess? So that's excellent. We're very close. Remember, so if I use 0.04, remember that functions that have a base is between 0 and 1, they are decreasing, right? Now, if you found me a credit card where I could just not pay it off and it decreases over time, please let me know because I would like to sign up for that one and maybe like 10 more of them. But no, so 0.04 doesn't quite work. Jillian, do you have an idea? But we're almost there. Thanks, AJ. Not negative 0.04. I'm going to give a little clue here. I'm going to erase the 0. And I'll give you even another hint in here. So what happens when you get an extra 4% on your balance? The balance the next month is 100% of your previous balance plus the extra 4%. Your new balance is 104% of what it was. And when you put, Julian? 1.04. Yeah. So 0.04 was excellent at 4% as a decimal, but you just got to make sure it's 1 because we have to add on that 4%. Are you guys okay with that? All right. Any finance problem like this, it's always going to be 1 plus when things are increasing. And now we can do how much will he have? How much will he have? I think I made that mistake 5 years ago, and I still haven't changed it. I probably won't until next year anyway, or even next year. How much will he have after 1 year is up? What are you guys plugging in for M? 12, yeah. So we just got to be mindful of our model was the amount after every month. This 4% is every month. So we're looking for 12. 12 months. 1 year equals 12 months. And then the expectation, again, for you guys is your calculators can do that happily in one step. Now, as I'm just doing this, realistically, a credit card company would not just let you not pay off your credit card bill. You would have to make some kind of minimum payment every month. But that's a topic for our financial math unit after the break. $4,002.58. Did you guys get that as well? Now that's actually this number is pretty realistic in terms of our credit card rate. Pay off your credit cards. Okay, in 1 year, and we're finished. And that wasn't so bad. I'm going to end the video. So long, YouTube.